Hello everyone, I am Boris Voskresenskii, Chief Digital Officer of Severstal, and today I want to share with you our data science approach to boost production in our factory. I will share with you two cases. The first one is about improving productivity of metallurgical pickling line with reinforcement learning. The second one uh, is about how we have used causal inference approach in MIL 5000. And in the last part of my presentation, I will tell you about our architecture of our data lake. And I should mention that these solutions are working in production, and they control key parameters of the units with the 24-hour per 7-day timeline. Let's start with metallurgical pickling line overview. I think that most of you know about it, but I should tell it. The metallurgical pickling line is a unit where you use acid in pickling baths to remove defects from the surface of the hot steel. You should pull your metal through baths continuously without stopping. So you weld your steel in the welding machine. Then you push your metal through pickling bath, and you cut your steel after that to receive clean and the high quality metal after that. What is the problem? If you put too much speed in pickling bath, you can have two situations. The first situation when you don't have enough metal in first looper, and the next situation if you have too much metal in the second looper. But you won't push the metal with maximum speed because of productivity of this line. So before us, the speed was put manually by the operator, and we want to improve it with machine learning or something like that. Let's tell you about our solution. We have used reinforcement learning approach here. First of all, we generate data about coils in this aggregate with GAN because we don't have enough information for reinforcement learning approach. So we should imitate this with GANs. Then we create a digital twin of our aggregate with about 100 parameters. Digital twin here is the model where you can choose the next speed of the central unit, and you receive what the 100 parameter will be after 1 second of this changing. And you can roll this process to the future. We have two agents here. The first is analytical agent. It's mathematical model uh, which use some logic to control the central unit, and reinforcement learning agent, which can train, which can learn what good and what is bad from a kinematic environment. So together they send their preferable speed to the kinematic environment, and kinematic environment tells them what is their reward and what is the state of the aggregate in the next second. Uh, because of this is digital twin, they can be very aggressive sometimes, but with the enough time, they can learn when they can be aggressive and when they can't. And after they learned it, we can use these agents and put them into the real life, because the digital twin is very close to the real unit. You can read about this approach in the link below. We have an article about it. And what is the result? The result is very impressive. We we could boost our unit by more than 6.5%, and we are receiving additionally about 100,000 tons per year. And this model in production since spring 2020. It's more than 1.5 years for now. The second case is about MIL 5000. You can see this unit on the slide. And here we have a different problem. We want to boost our productivity, but if we choose too much speed for the production process, we can lead to shutdown of the engines. And before us, as in the previous case, the speed of each iteration was set by a human. And we decided to improve it with machine learning. Of course, we can use large BM, but there is some problem. If we train it on historical data, we can learn not only how the physical process is, but also how the human is operating this unit. Because when people choose speed for the unit, they understand what speed can lead to what electric current. And also they can see what is the parameters of the aggregate for now and incorporate it to their decision. So if you use large BM model and then want to change velocity in this model as your control parameter, you don't receive very stable results. I don't suggest to use machine learning approach such as LightGBM in such problems. Usually you train a model of electric current with respect to velocity and other parameters. But you can do something different. You can train a model of velocity in respect to other parameters as function of z. And with this model, you can receive estimate of velocity corresponding to these parameters. And after that, you can split your dataset into the subsets where you can receive something very close to subset without high correlation of velocity and z. And after that, you can train usual models of electric currents as a function of velocities and other parameters. And with these models, one in each subset, you can receive derivatives of electric current by velocity. You can read about this case in the link below. There is some code and examples. And we combine this causal inference approach with machine learning approach with LightGBM. And this lead to very high productivity on our meal. For example, before our model, the maximum speed of the unit was 3.2 meters per second, and now the maximum speed is 4.5 meters per second. Also, we create a prediction model of the rolling time of the current group of slabs. And also this year we created a model which control heating process. So I think our unit is one of the most digital in the our company with this set of different models. Let's go to the architecture of our solutions because we control our units in real time. This architecture should be very safe and reliable. And but also it should very efficiently work with big data. So here you can see the center of our solutions. It's Kafka. It's Kafka is a broker of messages. It's our software bus. And from the units, we receive information by our producer. it's our self-made software with Java. Also, we use MiniPy for working with databases. And when we want to send something to our units, we use consumers, also Java software. And here, for example, OPC servers, such as OPC UA. You can use preprocessors to transform some data in Kafka. Also here, the brain of our solutions, some software in Python. Also, you can use user interfaces when you want to communicate with operators, for example. If you want to input some data to your models. And we use NiFi as our connector to Hadoop, for example, or to InfluxDB. All information from Kafka is stored into Hadoop. And with Spark, you can transform data in Hadoop. Our data scientists are working in edge nodes servers, where they can take data from Hadoop with PySpark and use it for model training. And I should tell you about this block. We use Grafana to visualize current situation in the unit. For example, we can monitor how often is our model working. I can share with you one fun fact. When we implemented our solution, not every team on the unit was very happy about it. And some teams used this model very often, but some teams are not. And we create a contest between teams. Which team are more using our model have received more money. And it's very efficient way to implement machine learning solutions in your factories, I think. As backend, we use InfluxDB for the Grafana. So thank you very much. I hope that this presentation was helpful for you. And I'm ready to answer your question.